Hi folks. So we've learned how to name and write formulas for molecular compounds, but we haven't learned the details of how to do Lewis diagrams for covalently bonded molecules. So again, to remind you of the octet rule, most atoms form bonds in order to have a full valence shell. And a full valence shell is usually considered to be 8 valence electrons. There are exceptions to that, but generally speaking, 8 valence electrons. The reason atoms do this is because it decreases their potential energy and increases the stability of the atom. Also, as a quick reminder, remember there's a pattern for, well, ion charges, but we're not doing ions today. There's a pattern for valence electrons. So you know how many valence electrons an atom has without thinking about it too much. If the atom is in group 1, it has 1 valence electron. If it's in group 13, it has 3 valence electrons. If it's in group 17, it has 7 valence electrons. Okay, so you can follow kind of these blue numbers here to help you predict the number of valence electrons in an atom. That 8 valence electron rule does not apply to every single element. There are some exceptions to this rule. Those exceptions are hydrogen. Hydrogen never has a full octet. Hydrogen is considered to have a full valence shell with just 2 valence electrons because it's in the first period. So hydrogen will only ever have at most 2 valence electrons around it because 2 is considered a full valence shell. Hydrogen atoms start with just 1 valence electron, but they're going to form bonds to get 2 valence electrons. Beryllium is another exception to the octet rule. Beryllium starts with 2 valence electrons, but it's going to form bonds in order to reach 4 valence electrons. So the maximum you tend to see for beryllium is about 4 valence electrons. Similarly for boron. Boron starts with 3 valence electrons, and it's going to form covalent bonds to reach up to 6 valence electrons, typically speaking. So how do we draw Lewis dot diagrams for covalent molecules? It's a 5-step process, so let's look at what the steps are. First, you need to find the total number of valence electrons. Second, you need to arrange the atoms so that the singular atom is in the middle. Next, or before I go next, there are a couple rules to guide you with placing these atoms. If carbon is present, it always goes in the middle. If hydrogen is present, it can never go in the middle because hydrogen, as we said on the previous slide, can only form 1 bond. So it can never be in the middle of a molecule. The third step is to form bonds between atoms, and covalent bonds are made up of 2 electrons. Then you distribute the remaining electrons so that you give each atom an octet of electrons, unless the atom isn't supposed to have an octet. Remember, I gave you 3 exceptions on the previous slide. Then, if there are not enough electrons to go around, you start to form double bonds or triple bonds. For the first examples we're only going to kind of go through steps 1 through 4, and then we'll add in some double and triple bond examples at the end. So let's do an example for carbon tetrafluoride. Now, 1 carbon has 4 valence electrons. Each fluoride has 7 valence electrons, and 4 times 7 is 28. So altogether, I have 32 valence electrons to place in my Lewis dot structure. That's step 1, count the valence electrons. Step 2 is to arrange the atom. Usually the singular atom goes in the middle, and in that case, that is carbon. So I'm going to put carbon in the middle, and I'm going to arrange the fluorines around it. Now, I draw the minimum number of bonds that I need to connect everybody together. And remember that each of those bonds, each covalent bond is made up of 2 electrons. So far, by drawing 4 bonds, that took 8 electrons. So out of the 32 electrons I said I had to draw, I've drawn 8 of them. So I have 24 electrons left to draw. Step 4 now is to divide up the remaining electrons so that every single atom gets a full valence shell. Carbon here already has a full valence shell because we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons around the carbon. So now I just need to fill in around the fluorine. And remember, I've got 24 electrons left. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I drew 24 electrons here, and every single atom in my diagram has 8 valence electrons. So this is the correct Lewis dot diagram for carbon tetrafluoride. Let's do another one, beryllium chloride. Beryllium has 2 valence electrons, and chlorine, each chlorine has 7 valence electrons, but we have 2 of them, so that's a total of 14. 14 plus 2 is 16 electrons to place in my Lewis dot diagram. Step 2, I need to arrange the atoms, and usually the singleton atom goes in the middle. So beryllium is going to go in the middle, chlorides go on either side. Step 3, form covalent bonds between the atoms, the kind of the minimum number of covalent bonds you need to actually make everything stick together. And here I've represented 1, 2, 3, 4 electrons. So I only have 12 electrons left to add to my diagram. Now, before I start filling in and working on step 5, it says step 5 is to give these remaining 12 electrons to all the atoms to give everyone a full octet. But I have to remember the exceptions to that rule. Beryllium is happy with just 4 electrons, and beryllium has its 1, 2, 3, 4 electrons. So beryllium doesn't get any more of these 12 electrons. Those 12 electrons go somewhere else. They go to the chlorines. So I'm going to give those remaining 12 electrons, 6 each, to each of the chlorines. And now all the atoms in this diagram have a full, either a full valence shell or the full number of electrons they're expected to have in the case of beryllium. More examples. It's time to pause the video and try these for yourself and then restart and see if you got them right. Ammonia, which you can call nitrogen trihydride. Ammonia has 8 total valence electrons, 5 from the nitrogen plus 1 plus 1 plus 1. And if we distribute, if we draw the picture, nitrogen goes in the middle, and hydrogens go around the outside. And then we draw 1, 2, 3 covalent bonds, each made up of 2 electrons. So I've got 2, 4, 6 electrons here. And I have to draw just 2 more electrons. And those 2 electrons do not go to the hydrogens because the hydrogens are happy with the 2 electrons that they already have. 1, 2 electrons for hydrogen, 1, 2 for hydrogen, 1, 2 for hydrogen. So those remaining 2 electrons both go on nitrogen because if I don't, now that I have those electrons there, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons associated with nitrogen. So all of these atoms have either a full valence shell, as is the case for nitrogen, or the maximum number of electrons that we expect them to have for hydrogen. The next example is boron trifluoride. And boron has 3 valence electrons, and fluorine has 7 valence electrons each times 3. So 21 plus 3 is 24 total valence electrons. Now, the trick here is remembering that boron is going to be happy with just 6 valence electrons. So it's not going to get the full octet. It's one of those exceptions to the rule. Boron does go in the middle of the molecule with fluorines arranged around the outside, and then we draw the minimum number of covalent bonds needed to attach everybody together. And when I draw those minimum number of bonds, that accounts for 6 of the 24 electrons. So now I have 18 electrons left to place. And boron is happy with the 1, 2, 3, 4, 5, 6 electrons it has around it. Therefore, I need to make sure that fluorine has a full octet as well. So each. So 1, 2, 3, 4, 5, 6. Add 6 to each fluorine atom, and then this is the correct Lewis dot structure for boron trifluoride. For the next compound, dihydrogen monosulfide. Each hydrogen contributes 1 valence electron, so that happens twice for the 2 hydrogens, and sulfur has 6 valence electrons. So this compound has 8 total valence electrons. Sulfur goes in the middle. And of course, the trick here again is that hydrogen doesn't get a full octet. So when we draw the minimum number of bonds, that's 2 electrons and 4 electrons. So I've used up 4 of the electrons, so I have 4 left to place. Hydrogen doesn't get any more electrons because it already has the 2 electrons we expect hydrogen to get. And so all 4 remaining electrons go around the sulfur. 1, 2, 3, 4 electrons. And now sulfur has a full octet. 1, 2, 3, 4, 5, 6, 7, 8 electrons. So what do we do about multiple bonds? I did mention when I gave you the 5-step process that we might need to form double or triple bonds. A double bond is a covalent bond with 2 pairs of shared electrons. So that's 4 shared electrons total. And a triple bond is a covalent bond with 3 pairs of shared electrons, 6 electrons shared total. So how do you handle these examples with multiple bonds? The process is still the same, at least to start. So for carbon dioxide, I have 1 carbon with 4 valence electrons, 2 carbons, each with 6 valence electrons. So my total number of valence electrons to place in the Lewis dot diagram is 16 electrons. The carbon is the singleton atom. Also, it's carbon, so carbon just always goes in the middle. And now I connect the atoms with the bare minimum number of covalent bonds. So in this case, I've placed 1, 2, 3, 4 electrons to connect the oxygens to the carbon. Now, what I want to do, this picture here has too many electrons in it. What I want to do is give everybody a full octet. I want oxygen to have a full octet. I want carbon to have a full octet. I want oxygen to have a full octet. But to do that, it would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons. And I only have 12 electrons left to place. So what I need to do is I need to remove some of those electrons and replace it with a double bond. And I'm going to do a recount and see if I've got the right number of electrons yet. Okay, now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 non-bonding electrons. That's still too many because I've used up 6 now in my covalent bond, and so I only have 10 left to place. So I need to make another double bond. So I'm taking these electrons away and replacing it with another double bond over here. So now I have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons. So I have 8 non-bonding electrons to place. And that's 1, 2, 3, 4, 5, 6, 7, 8. So now this picture shows 16 electrons total. Each atom has a full octet. Oxygen has 8 electrons around it. Carbon has 8 electrons around it. Oxygen has 8 electrons around it. So now this molecule satisfies the octet rule, and this is the correct structure for carbon dioxide. So let's look at some more examples with multiple covalent bonds. Nitrogen. Nitrogen gas, it's a diatomic molecule, has 10 total valence electrons, 5 from each of the nitrogen atoms. So how do I draw nitrogen to satisfy these conditions? In order to have a molecule where all the atoms have a complete octet, a full octet, I start with just the one bond, which is 2 electrons, but I can't put 6 electrons here and 6 electrons here because that would be 12 and that would be too many. So I draw a double bond, and that's 4 electrons total. And now I need to draw 1, 2, 3, 4 electrons, and 1, 2, 3, 4 electrons. 4 plus 4 plus 4 is 12, and that's still too many. So I'm going to draw a third covalent bond. And now this is 6 shared electrons. And nitrogen only needs a lone pair here and a lone pair here for each nitrogen to have a full octet. And that resulted from having that triple bond. Oxygen gas is another diatomic molecule. It has 12 total valence electrons, 6 from each of the oxygens. And I do a similar reasoning, a similar process for finding the double bond, finding out that this needs a multiple bond as well. So I start with just a single bond, which uses 2 electrons. So I still have 10 to place, but I would need 6 electrons on this oxygen and 6 electrons on this one to give each oxygen a full outer shell. 6 plus 6 is 12, and I don't have 12 electrons left. I only have 10 left. So I need more electrons. I'll draw in a second bond. This is now 4 shared electrons. Subtract 4 gives me 8 valence electrons left to place, and 8 electrons is exactly what I need to give the oxygens each a full octet by drawing 1, 2, 3, 4 pairs of non-bonding electrons. Both oxygen atoms have a full octet. For sulfur trioxide, sulfur trioxide has 24 total valence electrons, 6 from sulfur, 6 from each of the 3 oxygens. So when I start to place this, I put sulfur in the middle, oxygens around the outside, and I start by just drawing the minimum number of bonds needed to connect all the atoms together. Now, in order to give everyone a full octet, I've drawn 3 bonds, which is 6 electrons, so I have 18 electrons left to place. If I want to give everyone a full octet, I would need to put 6 electrons here, 6 here, 6 here, and 2 more here. That would be 20 electrons. I don't have 20 electrons, I only have 18 left. So I need to draw in a double bond. And now sulfur has a full octet. Oxygen just needs 2 more lone pairs of electrons. This oxygen needs 3 more pairs, and this oxygen needs 3 more pairs. So I have drawn 12, 16, 17, 18, 19, 20, 21, 22, 23, 24. I have drawn 24 valence electrons here, and so this is the correct structure.